Donc, oui, bonjour à tous et à toutes. Donc, je vais en fait présenter les travaux sur light field image coding using VVC standard and view synthesis based on dual discriminator GAN. En fait, ce travail, this work have been published in ICME 2020 last year. It was selected as one of the candidates for the best paper award, and it was then extended to a journal accepted at transaction on multimedia. So this work has been done in the context of the Nader Bakir thesis, who is now associate professor at Lebanese University. As usual, I will give the context and the challenges behind this work. So recently we have seen that, as we can see in the figure on the left, the market on augmented reality and virtual reality have increased significantly during the last year. And this is because this technology is used in many applications of prominent, like autonomous driving, entertainment, and healthcare, for example. And now we will see how we can generate a virtual reality using light field imaging technology. So first, what is light field? Light field is can be represented as a 7-dimensional function, as we can see here, L function, which is depends on 7 parameters, which are like x, y, z, the position of the viewer, theta and phi, which is the angle of the lights coming from different directions, and the wavelength lambda and the time t. So this light field function can be simplified in 5-dimensional function because the time can be sampled by the acquisition device depending on the frame rate. And the lambda can be represented in 3 components. Usually we use RGB color components. So there is also another representation which can simplify this 5-dimensional light field function into a 4-dimensional function. As you can see here, if we want to represent the light coming from this direction, it can be represented by 2 parallel planes, which have here 2 dimensions, x, y, and u, v. So this is the mainly used light field function, which can represent the lights coming from different direction in 5-dimensional with using the coordinates uv for the first plane and t. Yeah, here we use x, y, and uv for the second plane. So now we have seen the definition and the equation used for the acquisition of for the definition of the light fields. Now we will see like how we can have the acquisition of this image and video. So usually we have 2 main technology. So the first one is the multi-camera. Using a multi-camera, as we can see here, we can have an array of camera. With each camera we can have 1 view, and we can reconstruct a light field view with, as we can see here in this figure on the right. And we have 1 view giving a point of view from each viewing position from different camera. So this is the first technology, and the second technology is what we call the planoptic camera. So planoptic camera use different technology relying on micro lens. As we can see here in this figure, each micro lens have several pixels, and each pixel will capture the lights coming from different directions. And with this, the number of pixels in each micro lens, we will have like angular resolution, and the number of micro lens in the camera will give us the spatial resolution. As we can see here for each, as we can see here, like we can have different advantages of and drawbacks with using a multi-camera or planoptic camera. As we can see here, planoptic camera is more compact, but the baseline between different view in the planoptic camera is narrow. However, it can be different depending of the space that we can have between the different cameras. In this work, we will focus more on the planoptic camera. We will focus on the light field image acquired by the planoptic camera. So this light field imaging can provide many advantages. Like what we can do, we can have a refocusing capability of the image after acquisition that we cannot do with legacy cameras. We can also have a change of perspective with different views. And when this light field technology is coupled with head mounts, we can have a virtual reality with a better viewing experience, which is more realistic, representing a real 3D scene. So, however, there are many limitations, and the main limitation is the very large amount of data which is required for the storage and transmission of this light field imaging. For example, if we take an example of one light field image of Lightroom camera, it requires 1.5 gigabits, which is very high. Uh, and can be like a bottleneck for many applications because we have to store these images in video and we have also to transmit them. So also this high level of this high amount of data can also lead to a high computational processing and energy also. So we have to in this work we tackle these two problems by proposing an efficient and low complexity coding solution for light field image coding. So as we can see here in this scheme, so this is the transmission scheme of light field imaging. So we have acquisition, then pre-processing, then the coding, then the transmission, and then when the receiver will receive the light field image, it will be decoded. Then we can provide some post-processing before the viewing. And in this work will provide these two blocks in red, so the coding and the decoding, to reduce the amount of data required to represent the light field image at very high quality. So in this first section, I gave some introduction about what is light field imaging and what are the advantages and the limitation of this technology, and then how we can tackle this limitation of a very large amount of data with efficient coding solution in the transmission chain I illustrated just here. So now I will go to some related works. Of course, in light field coding, this last 5 years, there are many solutions have been proposed for the coding of the light field imaging. So we can have two categories here, as we can see in this figure, like lossless coding that enable lossless coding of light field images, and we have then lossy coding that encodes in lossy fashion the light field image. In this work, we focus more on the lossy coding, and in the lossy coding, there are several approaches also. So the first one is to apply the transform to compact the energy of the light field image and reduce the spatial and angular redundancies. The second category we can see here, which is also investigated a lot, is to represent this light field views in a pseudo video sequence and then use 2D video encoders to encode them. And the third category here, we can see like we use, it is predictive approach coding. The idea here is not to encode all the view, but enable to predict them with using a synthesis block, for example. Here we see three examples of this two last category. So the first one is colored light field compression for homography-based low rank approximation. It was proposed by INRIA, the team of Christine Guimau. So the idea here is to take the original light field views, as you can see here, and then you organize them into one matrix. So each view is represented in a vector, and then do some homography wrapping to remove the disparity between, or align the different view, or remove the disparity between the view. And then once we have this matrix with aligned view, we will apply what we call low rank approximation, that it is performed with this global optimization problem. So we try to minimize the distance, like here 4 billion distance, between the rapid light field images and its low rank decomposition into matrices B and C. And then only these two matrices B and C at K level k like k, for example, vectors or k singular values will be transmitted to the decoder, enabling to perform a very high level of compression. So this solution mainly focuses on homography and low rank approximation. So the second solution, it was proposed in 2016, is quite simple. So the idea here is to propose some ordering of the light fields views. So we take light field views, we perform some ordering. Here is, for example, spherical ordering to put them into a pseudo video sequence. And then the pseudo video sequence is encoded with a classical 2D video encoder. We can use AVC, HEVC, or any 2D encoders. And this is has the advantage to leverage the motion compensation solution that are provided by the encoder to decrease the angular and spatial redundancies within the light field image. And the third solution that combine 2D codings and also some linear prediction at the decoder side. So the idea here, as you can see here, we have the light field views, which is represented in two colors, so red and blue. So the red colors, this are called reference views. So the reference views are encoded with 2D video encoder. For example, it can be HEVC and transmitted to the decoder that uses the same encoder to decode them. Okay, and then this blue views are not transmitted, but are predicted from the red views. And how these blue views are predicted at the decoder side? They are predicted with using linear approximation. So from this red views, we put them in one matrix. And then for each blue views, we send one vector, xb, which is component are optimized to minimize the distance between the blue view, the original, and the one which is linearly recovered at the decoder side. So for each blue view, we will not send the view, but we send only this xb vector, which is composed by m component. And this vector will be then multiplied by this reference matrix at the decoder side to predict this blue view. And this solution also have a lot of, gives very good performance because actually we encode only half of the views by 2D encoders, which is efficient, and all other views which transmit only one vector of m component, which is very low, which requires very low rate, which equals very low rate, and it enables very high coding efficiency. So in this section, to summarize very quickly, we see like for light field coding, there are many solutions, and we have lossless and lossy. For the lossy coding solutions, we can have different categories. The one based on 2D encoders, the one they are used, for example, some prediction with using linear prediction or low rank approximation for the encoding. Now we will present the proposed solution. So the proposed solution is presented in this scheme. I will try to explain it clearly. So in this first part, we have the encoder, and in the second part, we have a decoder. So first, as you can see here, we have our light field view. Like each small rectangle here is one view. And this view are decomposed in two sets also. As you can see here, orange view represent the reference views, and all other views represent, blue views represent no reference views. And here, the reference views are carefully selected to be at the corner of each quad block of the light field image. So then how we will encode these reference views and these no reference views? First, at the encoder, they will be organized in several temporal layers. So as we can see here, this is the reference views organized in 3 temporal layers. and the no reference views in blue are organized in two temporal layers. So both reference and no reference are encoded by VVC encoder in this hierarchical coding representation into 5 temporal layers. And then the reference views are sent to the decoder. So the reference view encoded with VVC are sent to the decoder. Now for the other no reference views, they are sensitized by this green block, which is called the light field D2 GAN for dual discriminator GAN sensitizer. So all the no reference views here are also sensitized by this green block. And this red block will perform some rate distortion optimization between the view which is encoded by VVC and the one which is sensitized with this green block, and select the one that performs the highest rate distortion, the lowest rate distortion cost, which is sent to the decoder. So in this for the no reference views, we have two options. The first option is to encode it with VVC, and the second option is to sensitize it with this green block. When this view is sensitized with this green block, we don't send anything to the decoder. So it will be sensitized also at the decoder side. So I think it's clear. I hope it is clear for the encoder side. Now we will see how the solution performs at the decoder side. So at the decoder side, we will receive all the reference views, which are decoded with VVC decoder. So this is represent this three temporal layers views. And then these views are also fed this light field dual discriminator GAN, which will be able also to sensitize the views which are not transmitted by the encoder. So like the reference views, the no reference views here, which have not been transmitted by the encoder, will be sensitized by this green block. And then we have this two blocks. These two blocks, we will perform some quality enhancement only on the no reference views. And we will see later why we need this quality enhancement blocks. And this quality enhancement blocks takes one central view, which is this view, and the second view among the reference view. We will see this selection is done by a no reference quality metric. I don't know if it is clear for this scheme. So the idea is to have two sets of light field view. The one we call it a reference view and no reference view. So the reference view is encoded with VVC and transmitted to the decoder. The no reference view are whether encoded with VVC or sensitized with this light field D2 GAN. And this block, rate distortion optimization block, will decide if we have to transmit it or sensitize it. At the decoder side, we do inverse operation. First, decode all the views which are transmitted and encoded with VVC, and then sensitize the missing view. And then for the no reference view, perform some quality enhancement based on two reference view. And we will see later how to select this reference view and why we need to perform this quality enhancement block. So the main important component here are the light field D2 GAN sensitizer block, the rate distortion optimization block, and the quality enhancement block that I will present in the next slides. So first, this is the architecture of the synthesis block. It is composed mainly of one generator and two discriminator. So the generator is based only on two convolutional neural networks. So the first convolutional neural networks enable to estimate the disparity of the missing view, no reference view. And the second convolutional neural network will estimate the color, actually the RGB component of the image. And as input, here, as we can see in this light field image, each input, it takes the four corners of each quarter of the block, and it will be able to sensitize all the blue no reference view inside this part of the block of the light field image. And the training of this generator, which is composed by two convolution neural network, it will be guided by two discriminator, as we can see here. And the first discriminator, we will minimize the callback loss function. And the second discriminator will minimize the reverse of this callback loss function. As we can see here, it is a three-player minimization maximization problem. So the idea is to minimize the cost, minimize the loss function of the generator, and maximize the loss function of the two discriminator D1 and D2. And this loss function is given here as the weighted loss function of these three components. So this synthesis block will enable to synthesize all the no reference block, or no reference views, which are represented in the blue color. So now we will see how this reference and no reference views are encoded in a hierarchical coding architecture. Here we see like the group of picture, how these views are encoded with using VVC and temporal scalability. We have here the temporal layers in the GOP. For example, the first temporal layer, the second and the third will encode the reference views. And the temporal layer 3 and 4 will encode the no reference views. What we can see here, this arrows represent the prediction which is performed between the views. What we can see, like the reference views do not depend on the no reference views. So we can discard all these no reference views without impacting the decoding of the reference views, because they are not dependent on the reference views and they are encoded at lower temporal level. So here each temporal level, for example, 2, depends, the views in temporal level 2 depends only on the views which are encoded at lower temporal level, which are here temporal level 1 and 2, and so on. So this solution will enable us to be able to remove views from temporal layer 3 and 4 without impacting the decoding of temporal layer 0, 1, 2, which involves the reference views. So how we do this? So here we have this solution for the rate distortion optimization problem. So we have the reference views which are encoded at the three first temporal layers. So here we have 16 view that will feed the D2 GAN block, which will be able to synthesize 48 views. And the other no reference views are encoded, like this 48 views are also encoded with VVC at temporal layer 3 and 4. And this rate distortion optimization block will decide to encode with VVC or synthesize with the synthesizer block this 48 views at the encoder side. So if the video is better to encode with VVC, we will send the bit stream. If it is not, it is better to synthesize it, we will send nothing to the decoder, and the view will be synthesized at the decoder. And this will not impact the decoding of the other views because we use this hierarchical coding configuration. As we can hear, I give an illustration here. For example, here we have the temporal layer 4 and 3 at the step A. So for example, for this view, we will compute the rate distortion cost, which is equal to the distortion plus lambda, the rate. So if, for example, it's better to synthesize it, we will remove it from the VVC encoder, as we can see here in step B. Then we will test the other views, which is also at the temporal layer 4. If it is better to synthesize it, we will also remove it from the encoder. And then we will test the views which is encoded at the temporal layer 3. So if it is also better to transmit it by if it is better to sensitize it, we can also remove it without problem from the encoder. And what we have, there is here one constraint. For example, if we decide to keep one view at the temporal layer 4, so we don't go farther, because we have also to keep this views at temporal layer 3, because we need it to decode the views at the temporal layer 3. So once we keep one view at temporal layer 4, for example, we have also to keep all the views at lower temporal layers. So now I presented like the two first components. So the first one is the block synthesis, and the second one is the rate distortion optimization algorithm, which is also given here on the left, that's enabled to decide for each views, no reference views, if we should encode it with VVC or we should sensitize it at the decoder side. Now, the third block is the quality enhancement block. So why quality enhancement block is important? Because when we decode these views, one view may come from VVC and one view may come from the view synthesis. We can have a high disparity in terms of quality. And with this quality enhancement block, we want to propagate the quality from the views which are encoded at high quality to the views which are sensitized or coded at lower quality. So this quality enhancement block is performed only on the no reference views, and it takes as input 3 views, as we can see here. So the first view is the central view. Why central view is important? Because it is a reference view and it is encoded at by Antra coding, so it always have the highest quality. The second view is the target view VT, the view that we want to enhance. And the third view is another view from the reference views also, and which is decoded at the highest quality. And how we select this view, we perform some novel reference quality metrics among all the reference view, and select the one that performs the highest quality. And because the idea here is to propagate the quality from the central view and this other view, reference view, which have higher quality, to this target view. And this quality enhancement network, which is called here MV QualNet, it's perform two stage. So the first stage is with using convolutional networks. It performs some features extraction, which are then concatenated, and this go to the densely connected mapping, which enable to construct the residual of this missing view. And once we have the residual, we add to the residual this target view to construct a target view at higher quality. So we will see, and this network, it is trained in it is trained by trying to minimize the difference between this reconstructed view, enhanced view, and the reference view, like the original view before encoding. And as we can see here in this figure, it is important to perform this quality enhancement stage. As what this figure gives, it gives the PSNR for the different views of the light field image. Here we have 64 views. As we can see here, the highest bound which are here are the reference views which are encoded with VVC. And these 3 colors, blue, red, and green, represent the configuration where all views are encoded with VVC. And this is the solution which perform a rate distortion between VVC and view synthesis, but without this quality enhancement block. And the green curves, it's with this quality enhancement block. What we can see here, this highest bound are the views which are encoded with VVC. The same quality are for the 3 solution. Then we can see for example, for the red curves, that for the no reference view, the quality is enhanced because of the rate distortion optimization that's enabled to take the highest quality between the views decoded by VVC or the views synthesized by the D2 GAN. And what we can see also with this quality enhancement, it's enabled to enhance the PSNR quality of these views decoded in red with using this quality enhancement block. And here we have two advantages to perform quality enhancement. The first one, we increase the global quality of the light field views, especially for the no reference views. And also we decrease the disparity of quality between the views. And this may lead to a higher quality of experience when we see the light field image. So this figure show why it is important to perform this quality enhancement block. And now we will see, once we presented this solution, which is composed in three components, like view synthesis, rate distortion optimization to decide whether we need to encode or synthesize, and the quality enhancement block. Now we will try to assess the performance of this solution. So to train this network, so for the quality enhancement and for the synthesis view, we use three different data sets from, so the first from EPFL, and the second one from Stanford University, and third one from HCI dataset. So each frame, it is split into patches of size 60 by 60 pixel, which leads to more than 150,000 patches. And here gives some of the parameters which are used to train D2 GAN network. For the testing, we took here 9 light field images, so 6 from EPFL, 1 from Stanford, and 2 from HCI. Illustration of these images are given here, and it should be noted that these images are not included in the training phase. So in this figure, I give here 6 figure for 6 light field images, giving the performance of our proposed solution with quality enhancement in the green color. And this figures gives the PSNR with respect to the bitrate. And as we can see here, our solution is compared to many other solutions. We can see like our solution perform always the highest PSNR quality for the 6 light field images at different level of the bitrates. And also we can compare it to the solution which is represented here in red, which is exactly the same than our solution, but without this quality enhancement block. And we see here the gap that this quality enhancement block, the gap in improving the quality between the red and the green color. To be clear, like this red color configuration was proposed to the ACME conference, and the red color configuration, the green color configuration, it was the extension to the journal, and we show here a clear improvements in terms of PSNR quality for the 6 light field images. And we compare to many solution, state-of-the-art solution, and we are reaching always the highest PSNR quality. Now, when we computed also the bitrate. So the bitrate in terms of, it gives us like the bitrate saving when we see here bitrate saving, and the PSNR enhancements over 4 pounds of bitrate. And we compared our solution here without quality enhancement and here with quality enhancement with respect to the solution proposed by Liu in 2016. And in comparison also with the solution using VVC for all the views and using these 2 solutions proposed in 2018 and 2019. We can see here the top 1 scores are represented in red color, which are given by our solution with quality enhancement, and the top 2 score are given by our solution without quality enhancement. And we can see here, compared to this solution proposed in 2016, we can perform up to 36% of bitrate saving and around 1.35 of PSNR increase for this 9 light field images, which is quite significant for the coding of light field image like research. Now I will give here some visual illustration of two light field images. So the first one here is danger de mort encoded at 0.32 bit per pixel. Here is our solution without quality enhancement. And here it is for also the second image, which is desktop. We can see like these views both are synthesized by our D2 GAN synthesizer block. We can see that the quality is very good and it is very close to the original image, which is represented here. The PSNR also is higher for compared to the other solution which are represented here. And we keep also all the details of the original image and also the colors. Even if we synthesize the images, the colors are quite consistent with the original frames. So now, when it comes to complexity, here we provide some numbers about the complexity of the encoder and the decoder. So the first table here is giving the runtime encoder in second, and the second table is giving the runtime also in second. As we can see, the complexity, we give the complexity on CPU and GPU. We can see like the complexity has been increased compared, for example, to the configuration where we use only VVC. Why? It is because at the encoder side, we perform both encoding with VVC and also decoding, and we perform like the view synthesis, all the no reference views, which increase significantly the encoder complexity, but it remains low complex that this configuration, for example, that use the GEM reference software, which is also quite complex. And this complexity number are provided here for different quantization parameters. So at the encoder side, we don't perform quality enhancement, so we don't have the complexity of this component. And at the decoder side, so for our solution, I provide here two numbers. So the first number in green is without the without the quality enhancement block, and the red color block is our solution with this quality enhancement block. What we can see here also is that the quality enhancement block increases significantly the decoding complexity. But it can be decreased a little bit with using GPU, for example. But here we really need to do more optimization and parallel decoding. For example, this quality enhancement can be performed in parallel with the decoding of the reference views, which are not selected as a reference for the quality enhancement block, to reduce this decoding time overhead. So to conclude this section, we have presented the performance in terms of PSNR. We have some BD rate, BD PSNR, and we show some visual illustration and also some complexity results for both encoder and decoder. So to summarize and conclude this work, so we have proposed a dual discriminator GAN model to synthesize the light field view, which perform a very accurate and good synthesizing performance. And then this scheme has been integrated in the coding solution to perform with a rate distortion optimization block, whether encoding with VVC or synthesizing with this light field synthesized block. And we also added a quality enhancement block at the decoder side that enable both to enhance the quality of the no reference views and also to reduce the variance in quality between the decoded views, which enable to enhance the quality of experience of the light field image. And there are still some open questions we can highlight here. Usually when we do encoding, we always try to encode and we don't trust like synthesizing. Now we have shown in this work that with using synthesizing as a decoder side, we can have a good coding performance also, but the question between encoding and synthesizing is still open. And with using, for example, a rate distortion optimization block, we can select which one is the best. And here we focus more on efficient coding of the views. As you may see here, I don't talk about the depth information in the light field images, which is also important. But we believe if we are able to decode views at a high quality, we can then estimate the depth at high quality to have to target some application where we need the depth information. And the last point is to validate the performance of our solution. We have also to perform some subjective evaluation to see what is the real improvements subjectively to the viewers in terms of immersive with using this technology. So the last slide. So I will share with you this video and this link. We can click on this paper. We will show like the web page of this paper. We will find more information and especially a demo when we can see different configuration of the decoded views, which is also like invent you can go to find more information about this paper. And yeah, that's all. And thank you for your listening. And yeah, I will be happy to answer your questions.
Thank you very much. I can begin the questions if you want.
Okay.
I have a first one. In slide 24, when you present the results on the bitrate of the different solutions, I'm not sure I had enough time to read the table. I think I remember that the bitrate of the solution with the quality optimization was lower than the one without the quality optimization. Is that right?
The quality here in green is the proposed one.
It was the slide after this one, sorry. The one with the table where you have the, okay. Yes, this one. So the bit rate of the, when you have the quality enhancement, is it lower than the one without?
Actually here it's, when we talk about bitrate,
yes,
we take the area under, for example, if you want to compare this solution in green, we want to compare it with this solution in the blue. Okay. We take the area between these two curves. So even if it is, the results are given in terms of rate or PSNR, but in this number, we consider both the rate and the distortion. Okay. For this reason, we can see here we have saving in terms of rate, but this rate does not come from saving of the rate because the rate is exactly the same. It comes from the increase in terms of quality.
Okay, this is what I wanted to confirm. Okay, I have another question actually. On the next slide, when you mentioned the time spent in the encoder and the decoder for the different solutions, do you have roughly an idea of how much time you are spending in the neural network in the decoder, especially because the time seems to be quite long for the decoding of a single image, and so do you know approximately how much time you spend in this part of the decoding process?
Yes, well, we have get this question from the reviewers in multimedia, and we give some nice results with giving like the complexity of each component. And here I can also answer to your question by some numbers here. If you can see here, for example, 4 is the complexity of VVC to decode all the views. And here, when we give the number, for example, 124, so we can see like we spend 120 for the synthesis block and 4 for the decoding with using VVC. So the complexity of the synthesis block is very high. And here we can say like 90 seconds is spent for the quality for the synthesis, and 4 it's for the decoding with VVC. Now, if we take this number in red, so the difference between the red and the green, it gives us the time we spent on the quality enhancement block, which is also quite complex. Like it's more than 2 times the times required to synthesize and decode with VVC. But here we just report some numbers to see like a magnitude about the complexity, but like we don't perform any optimization to try to enhance these numbers.
Thank you.
Another question exactly on this runtime and everything. What I find very interesting is that you've increased by 50 maybe the complexity of your decoding, for example. Could you just, I don't know, turn some knobs on VVC to make it compress by using much more complexity to gain as much bitrate? Could you increase the complexity of VVC to have the same gain in terms of bitrate?
Actually, what we have to see, like to answer to your question, these gains are not overlapping. Like we can increase the complexity of VVC, so we can reduce the bitrate or we can enhance the quality. So this gain, which is given by our solution, is in addition to what can perform VVC. I mean, even VVC is more complex and provide highest quality. So for our solution, maybe it can behave a little bit different, but this gain we show here, it will be always here because because even if, so for example, VVC will provide higher quality at higher complexity, so we will gain in terms of quality. So our synthesizer will be more efficient because the reference view which are used as input are at higher quality. Or if we reduce the bitrate, we will also gain it with our solution because we always perform this rate distortion optimization. And if, for example, it is better to use VVC, our rate distortion optimization block will prefer to send VVC. And this is the problem with learning-based quality enhancement or synthesis solutions. For example, when you train them on one data set, and usually when you test in the reality, we can give a poor performance. However, VVC, it's more reliable. For example, it may work, it's generalized better. So this rate distortion optimization block is very important because it will be always selects the solution that performs the highest solution and whatever what we have as a solution for quality enhancement or VVC encoding. I don't know if I answered to your solution, but
you answer a big part. The only thing that I was trying to get is to balance the complexity. Let's say if you remove all of your work and you make VVC encode very aggressively with a high complexity, could you gain as much bitrate?
Yeah, I think yeah, I can give you others answer. If you see here, like the gain of 36 we performed here compared to this solution. Like all the tools of VVC compared, for example, to HEVC are able to do this gain, actually, about 40%. So for this reason, I don't think if we fine-tune VVC, we can still able to double its gain. We can maybe gain 1%, 2%, or 3% over VVC, but we cannot gain this 36 because this 36 is really what VVC gain compared to HEVC, like all the tools. So now if we make VVC more complex, we can maybe gain 1% to 5%, but not 36. It is very high. Like to give you an example, it is equivalent to what VVC can gain compared to HEVC. Like it's the whole standard are able to reach these numbers.
Okay, thanks. That answered my question.
If there are more questions,
we have a question in the chat from Luce.
okay, I will try to read it. Je dois partir j'avais une question. Quelle est la proportion du choix RDO, VVC et GAN? C'est-à-dire, est-ce que la production temporale de VVC? Yeah, it's good questions. I don't have exact numbers of that. But I think we did some experiments. It may represent maybe, it depends on the sequence, because some light field images are very easy to sensitize, especially when disparity is low between the different views. So we can reach up to 90% of the views which are sensitized. But for other light field images where the disparity is high between the views, we can go to 20% of the light field which are sensitized.
I have another question on the rate optimization, the RDO process, the optimization process. If I understood correctly, the quality enhancement is not done on the encoder side before selecting between the VVC or the GAN image. Is that right?
Actually, this quality, the quality enhancement or the view?
The quality enhancement.
Yeah, quality enhancement is only decoder.
Okay, and wouldn't it be interesting from the bitrate point of view to do it also on the encoder side? Because if it helps you to increase the quality of the image synthesized by the GAN network, then maybe you could transmit even less information and trust the GAN to do more.
Yeah, because actually when we do this quality actually when you do sorry, yeah, when we vous m'entendez? Okay. Actually, when you do this quality enhancement, the only way to benefit from it at the encoder side is to use these views as a reference for either sensitizing or encoding other views. And in our solution, we added this at the decoder only to enhance the quality, are not used as a reference. So it may be interesting if we give this enhanced quality to the synthesis block or to VVC to use them as a reference for other views. So if they are used for other views, yes, but in terms of balance, in terms of complexity, we have to think if it is if it's worth or not.
Okay, to make it work at the, if I understand correctly, to make it work at the encoder side, you will need some kind of iterative process where you select the images iteratively. Okay, I will try with this one and this one as the GAN and this one as a VVC, do the quality enhancement and iterate the selection process to find the best combination.
Yes, and this like will increase the complexity. Like we don't, here we want to add something simple, and what we want really is to balance the quality between the views, because we have seen that no reference views does not reach high quality. So when you have like a difference in quality between views, it's not good for the global quality of the light field image. So this was the objective of this quality enhancement block. So if you added it to the encoder, we should increase the complexity and also give this enhancement views to other blocks to benefit from this.
Okay, that's very clear. Thank you.
Okay, we have 1 minute or 2 minutes if you have more questions, or we can close this session. I hope it was clear and interesting to hear about this light field image coding. It is now a hot topic, and it is presented as like the technology of the future in imaging. But as you can see, we are facing many problems in terms of the amount of data and processing complexity.
It's surprising that it's not presented as a future, because I remember the litro camera it was 7 years ago that I saw it on the shelf.
Yeah, it was bought by Google now. So for this reason, we don't hear about it a lot. But yeah, I think this technology, for example, because we have narrow baseline, we have different application. For example, even if we want to change the views, the disparity is not large between the views. So we can, for example, have some focusing after acquisition. But there are many limitations in terms of both acquisition, processing, and also coding. Um, I think it's still in the research stage. There is also other technology which is called Pound Cloud, which reaches maybe earlier stage, a higher stage in terms of industrialization. But yeah, we'll see in the future what will happen. It's difficult to predict. Yeah.
Thanks anyway. That was very interesting.
Yeah. So thank you for your listening, and I think we can close the session and have a nice evening.